Welcome all to today's RSRG World webinar. We have the 3rd of March 2021 and we are streaming from Stuttgart in Germany. Thank you for being with us. First of all, let me quickly introduce myself. My name is Sven Schran and I am coordinating with RSIG our European locations. RSRG is now 3.5 years old and I joined a bit more than 2 years ago. I have worked in the automotive industry just for more than 13 years and started to take care about automotive security more than 4 years ago. Today, I work as product security officer in engineering of complex sensors for the robot Bosch GmbH, which is one of the biggest suppliers in the world. Just quickly, the Automotive Security Research Group, or shortly RSRG, is a non-profit organization focusing on the advancement of the automotive security industry. It is an open community to support the combining of two complex areas of competencies, IT security and the automotive business. This community is for you, the automotive engineer, the IT security specialist, the security researcher, the beginner, the hobbyist, even for the people that are in the wrong YouTube channel. The entire organization is built on volunteer efforts of the administrative team and of course yourself. RSRG is mainly based on 3 important pillars which represent our core values: sharing knowledge, enabling networking, and valuable collaborations. We are trying to remove the boundaries that can occur in the automotive security industry. This means, for example, communicating about relevant publicly available information, finding ways to learn together, finding good solutions, making best decisions, because at the end of the day, we all together have a joint purpose to keep our customers, our families, our friends' data safe and secure when they are using automotive related products or services, and this can only be achieved together. If you want to get more involved, make an impact on the industry, start your own RSRG location, participate in a technical committee, or be a part of one of our projects, please reach out to us. You'll find more information about RSRG at our website www.rsrg.io or send us just an email at hello@rsrg.io. One of our projects is to develop an automotive security vulnerability management program. RSRG is looking to make resources available which are necessary to ensure good security implementations. One of the most important topics during the development of a component, a system, a vehicle, or a service is to understand which vulnerabilities are existing. So we as a community of developers, testers, hackers, researchers, and hobbyists can make sure to fix, close, or solve the existing security vulnerabilities before an exploitation leads to critical damage like recall or even worse, a safety issue. At RSRG, we think it was the utmost importance to have an open vulnerability management system where we can ensure that the right people have the needed information. We need your help to derive important requirements for our project. Please take the time to fill out the survey we prepared together with Cybellum. The link is also available in the description below to this live stream. RSRG is just available around the globe. Today, we are present in 38 locations in 20 countries, and we just reached more than 6,400 members, which is really amazing. On average, we have grown around 15% a month since RSRG was founded, and this trend continues steadily. Please check out if your hometown is just part of our network. If this is the case, you are welcome to join our local representation. If you don't find a location near to you for now, but you think it would make sense to have an RSRG location in your city as well, don't hesitate and contact us. Before we come to our main presentation, I like to give an outlook to the next weeks, where we have again very interesting presentations, which we will provide to you via our RSRG World Webinar live streams. At March 11th, we will have a presentation about the AUTOSAR-based solution for an automotive IDS presented by Dr. Metzger from Vector. On March 18th, we will have a presentation from Tobias Madel from Fraunhofer ISAC regarding distributed trust level concept for autonomous cooperative vehicle networks. Then on March 25th, we will hear a presentation from TÜV Süd, which is an authorized technical service which can provide a vehicle type approval regarding the new UN regulations, and they will present to us vehicle conformity versus cybersecurity challenges for the automotive industry. Then on 1st of April, we will have a presentation from Bogdan Gradinaro from the company Clockworks. He will present automotive security for engineers with functional safety background. And finally, on 8th of April, we will have a presentation from Ken Munro. He is from Pentest Partners, and he will talk about vulnerability disclosure programs, how to make a VDP work. Great presentations. If you think you have a topic as well, which is related to security and automotive, and you would like to present it to our community, please contact us with your idea via cfp@rsrg.io. Now it is enough from my time, from my side, and I don't want to keep you tortured anymore because I'm sure you are waiting, very curious for our main presentation. Like every time, in case you have questions during the presentation, please write it in the chat window. After the main presentation, we will have a Q&A session where we will ask Hugues. Now it is my pleasure to welcome Hugues Thiebeauld, the founder and CEO of eShard, and he will present to us attacking SoCs by sidechannel or laser fold injection, a Graal's quest. Hugues, the virtual stage is yours.
Thank you, Sven. So good morning, good afternoon, good evening to all of you. I'm very glad to be with you today and to make this presentation for ESRG. So indeed, my name is Hugues Thiebeauld. So I am CEO and founder of Ishan. So Ishan is a security cyber specialist in embedded security. So our areas of expertise are both the integrated circuit security and mobile application security. So we are providing testing solutions, expertise lab services, and training for any kind of physical attacks in integrated circuits like sidechannel, fault injection, and we are working currently on photo emission and thermal laser stimulation. On my side, I have 20 years of experience in sidechannel and fault injection. So I am not very old. It's just that I started my career straight in this area. So this is why I have so many experience in this area, but I'm still young. So today I'm going to focus on this important topic. It's all about SoC, so system on chip. And you may ask to yourself, okay, what is the risk of physical attack like sidechannel or fault injection when it comes to SoC? Is it an overkill? Or in other words, do you have to take into consideration these attacks when you build your product or you design your chip? At the end of this talk, I hope that the answer for you will be yes, you need to take this into consideration. So I'm going to show you how this kind of attack can be done in practice, and both sidechannel and laser fault injection. I'm going to show you that they are not that obvious to set up in practice. However, their exploitation is quite efficient. So the whole purpose of my talk is to give you this insight so that you can take the right decisions on your side. So yes, attacking a SoC with sidechannel or laser fault injection is a kind of a Graal's quest, but it's not an unaffordable Graal's quest. So if you are ready for the drive, let's start to see how much we can overcome the different obstacles to make a successful attack, and see how much a secret key can be compromised. So you will see that all my examples after that are based on a practical experience on various I would say projects we have been working on. So they are all practical feedback I'm going to share with you. They are all targeting I would say AES implementations. Sometimes are software based, sometimes they are hardware based. But you will see that for all of them, there are plenty of obstacles. So let me talk about this during this talk. Maybe before starting, I should maybe shortly introduce what a sidechannel is, because I don't know how familiar you are all with this notion. So if I can manage to explain in 2 minutes, I will do my job for today. So let's say that you have a product and there is a SoC or there is an IC on this product. And this product is supposed to implement a security functions. When it implements a security function, you have a cryptographic, you will have cryptographic operation operating into this device. And if there is a cryptographic operation, there is a secret key. And we can assume that this device is exposed. So exposed because it's outside a secure world, right? So it's in the wild world, if you want. So the whole thing is that when the cryptographic operation will be executed, the secret key will be used to execute the cryptographic operation. And the sidechannel is leverage the ability for someone to get this side channel, which more or less will aim at collecting at monitoring the cryptographic operations when it's being executed by the device. If you can have a way to monitor this internal activity when the cryptographic operation is being executed, you may find some little bits of information that is related to the intermediate data of your cryptographic algorithm. And because there are little bits of information, by applying some statistical and signal processing tools, you can have a large amount of instance of this kind of sidechannel signal or sidechannel trace, and you can then get from these little bits the value of the secret key. So you may tell me, but I don't understand because the cryptographic algorithm has been chosen to be resistant against any kind of attack. But remember that it's the resistance is designed to withstand attacks when you know the message, when you get the ciphertext, and you don't know the key, and the secret remains secret. Here, you have intermediate data. And when you can have an insight of the intermediate data, this means that you can have an insight of partial value of the key. And this is possible for the hacker to get this secret by doing that. Okay, so what is the nature of this sidechannel trace you can get? Historically, when the sidechannel were introduced, there were mostly the power fluctuations. This explains why you may have heard about SPA or DPA attacks, but the P stands for power. But actually, there are some other ways to collect these insights inside the inside the secure device. So one classical technique now used is a near-field electromagnetic probe in order to collect the electromagnetic radiation around a little surface on the die. And more recently, if you follow the state of the art, some people have been publishing about what we name cross-channel techniques, where actually someone can leverage internal sensor in the chip in order to get some information from the internal activity, and they demonstrated that they could retrieve the secret key via the information available on this sensor. These latest publications are very important because it shows that even a sidechannel can be done remotely. When it goes to power or near-field electromagnetic, you needed a physical access to the device. But at the end, it looks very complicated. Is it science fiction? Is it a real risk? Actually, if you do this well, and knowing how to do it, a few minutes may be necessary only for a non-protected device to retrieve the full secret key. So actually, it is a real risk. It's up to you to know whether a given secret key compromise, how much it harms your system. It's very dependent on your system, right? But it can compromise encryption, authentication, integrity, or authenticity mechanism. So it may have a lot of impact. If you are on the chip manufacturer side, when you design a chip, you don't know exactly how your chip will be used. So you have to take into account the worst case scenario. When you are at the device, I would say, device manufacturer level or at the product manufacturing level, you know the risk, and so you are able to create your risk analysis and to know how harmful, so how much you have to protect this specific asset. Okay, so in real world, a practical sidechannel setup is typically that. So this is a picture of our own setup in Ishan. But what is behind? What is behind is, let's talk about money. Okay, I would say if you are a hacker, you can create a kind of a few thousand of your worth of equipment, and you can make the attack. At one point, we were even able on the smartphone to create an attack, a successful attack with less than 1,000 euros. But it's still garage work. Here, I'm not talking to hackers. I'm talking to you who are designing product and you want to do it seriously. What I would say is, if you want to do it seriously and if you want to build the expertise in-house, you will have to consider a budget between 50 kilo euro to 200 kilo euros, depending on how far you want to go and the level of equipment you want to use. So let's talk about the equipment, both hardware and software. First, one piece of equipment, very important, is a high-end oscilloscope, because this will be the main instrument to collect the data trace. Okay, it has to be clean. After that, usually, and particularly on SoC device, you have to use a near-field electromagnetic probe. So with a near-field electromagnetic probe, actually, you can even get the power fluctuation if you put your probe near the decoupling capacitor. Typically, that's not a great choice. I would say that's not the best choice, because at the decoupling capacitor, you will have, I would say, the information from the whole SoC, and we'll see later that an SoC is a lot of operation running in parallel, so you may be overwhelmed by the activity. A better practice is to do a local measurement on one part of the die, and for this you will position your near-field electromagnetic probe where the signal is interesting. The closer you can go to the die, the better the results, but it depends if you are able to depackage or not the device, the chip. You will need a XY stage, automated preferably, in order to make sure that you can do some scanning and you can have a good control of the location. You will need a software to drive the whole thing. It's very important because you may spend, I would say, 1/3 to do the data collection and 2/3 or sometimes 3/4 of your time to do the analysis on the traces. Because there is not one thing to try. Doing sidechannel is doing a lot of experimentation in order to find your way. This explains why at the end you need practical experience. And particularly on SoC, this will be necessary. Good. So now we are able to. Now we set up the bench together. Let's start with the first challenge. So the first challenge, I think, is quite easy to understand. It's the size of the die. A SoC device is big. So here I share with you an example. It's a SoC from a mobile phone, and this one is 8 millimeter times 9 millimeter big. So we mean 72 square millimeters. This chip is a 32 nanometer technology. So not the very latest, but not too bad. So in order to give an order of magnitude of what is how big is an integrated AES processor compared to this big SoC, I try to put some figures on it. So a 32 nanometer on the left, you can read the red text. A 32 nanometer is typically 3 millions of gates per square millimeter. This means that all in all on this SoC, you will have 216 millions of gates approximately. Now, if we are thinking about how big is an integrated AES, so it's very dependent on the manufacturer, on the designer, and so on, of course. But relying on this publication from Axel Poschmann, where the source is given here, sidechannel resistant crypto for less than 2,300 gates, I will assume that an integrated protected AES is between 5 to 15 kilo gates. Assuming that, this means that it represents 0.007% of the die, of the surface of the die, or 50 times 100 micrometer. So it's very tiny compared to the whole thing. So we want to do a near field, we want to use a near field electromagnetic probe, right? So how big, how much I can collect this tiny piece of information in this whole thing. So I made this effort for you. So I use some reference of electromagnetic probe designed by Langer. Langer is a German company. And you have different resolutions that are typically used for by specialists in sidechannel. So the first one concerns the probe RF3 mini probe. This one is not very expensive. Sorry, it's about 1,000 € with the preamplifier. So it's not a big price. And the resolution is around 1 square millimeter. So 1 square millimeter, I try to put for your reference, 1 square millimeter will be my gray square here in the middle. And the gray, this gray square, I put it on the chip. You see above. So you can have an idea of how big is 1 square millimeter on the whole thing. Actually, it's quite a lot. You imagine the number of gates you have underneath. Some other probes have a better resolutions. So talking about ICR probes, here I put 2 probes, respectively 500 square micrometer and 150 square micrometer. And you will have respectively the resolution in orange and the resolution in blue. And you can see that the blue is quite tiny and may cover or encompass a small part of the device. So how many gates I will cover with this resolution? So here you have the table at the bottom here. So you have the 3 probe, RF3 Mini, ICR 500 and ICR 150. And you can see that the number of gates for a 32 nanometer SoC device will be respectively 2.35 millions of gates for the RF3 Mini, 212,000 for the ICR 500, and 23 kilo for the ICR 150. 23 kilo, if you remember, just above, I was talking about an integrated protected AES around 5 to 15 kilo. So that's fairly good, actually. If I can manage this kind of resolution and I am exactly on the right part of the chip, I will have the whole AES, but I won't be too much noise by what is executed around, supposedly. But you may tell me, okay, this is not the latest technology. What about the very latest? So if you take the very latest from TSMC, today we are reaching 5 nanometers. I think TSMC is one of the unique manufacturers able to go to that technology. If you take this, my 3 resolution will cover 135 millions of gates for the RF3 Mini, 12.1 millions for the ICR 500, and 1.3 millions for the ICR 150. So 1.3 millions is much more than my 15 kilo gates, right? So is it a game over? No, it's not game over. It's not game over because you don't need to only cover this part. You have to assume that, yes, indeed, you will have more signals than only the integrated AES. So the bigger the resolution, the more noise. But that doesn't mean the information won't be there. You may need more traces to collect, to get the information, but that's still possible. So the risk is there, regardless of the technology. Okay, so let's say that I made my choice regarding the probe, the near-field electromagnetic probe, but where should I put my probe on the die? The playground is massive, right? So here I show one example, but you have different solutions for this. So one example, here we had a bit of fun by doing some thermal, infrared thermal analysis. So basically, what did we do is with a specific bench, we did a lot of successive AES, like AES, no AES, AES, no AES, like a command doing a lot of AES like this. And another one where we made no AES. Actually, the purpose of this is when you do a lot of AES execution, the gates will be activated and they will warm up. When you don't use them, there is no reason why they would warm up. And by doing a differential analysis, you have the picture on the right, and that shows a kind of heat map where the gates were activated. So here we can see roughly, like we have a bit of activity at the CPU level. It's normal because the CPU is calling the special registers, right? By looking at this, I would even say that I'm quite confident that the CPU, the core 0 was used because you have the core 0 here, the core 1 here, the core 2 here, and the core 3 here. And we can see that in this part of the glue logic, it's very red, so this means that the activity was high, right? So we can assume that approximately the integrated AES will be around this area. Great, but that's not very accurate, right? You can also consider photo emission. So I don't show an example today for this, but a photo emission technique may be useful as well to detect the active area on the chip. Okay, particularly if you have a photo emission with a photo detector in order to frame your analysis on a specific time. But with this rough idea of where it is, you may be willing to do, I would say, a more, I would say, fine analysis. And for this, we decided to build a cartography. And building a cartography is you will use your XY stage, and at each point of your scan, you will collect thousands of traces with the same secret key, but using different messages, typically, is one technique. And after that, you may have a statistical criteria in order to monitor if the valuable information can be found. Okay, let's see what we did. So here, I show you the outcome of one of these scans on the chip. So you have the picture of the chip, and here I can zoom up. Here we go. Okay, so as you can see, we are in backside. Okay, so you can see the surface of the silicon is like a mirror. And here I put on top of it a layer of our scan. So here we decided to scan more or less 1/4 of the device, which took quite a lot of time. And on each one, you have a point that we can select. And with 5,000 of traces, we applied different statistical operation. So here on the right, you can see each time what's going on. So you have the raw signal on top left. On top right, you have the average AES signal. So many times the same signal but averaged. The same when no AES was executed. This one is to avoid false positive. And on the bottom left, you have the t-test in order to see if there is valuable information. You can see that after that, our mapping is created so that each time we click the brightest, the more suspected information is there. Okay, so as you can see here, we want to click on. There are different sweet spots. We can go here, typically, and we can see that this is not great. We can see that the t-test is showing some valuable information, but the other traces are not very good, I would say. Actually, the sweetest spot is around these parts. And here, definitely we can cause that the t-test is reacting very strongly. That sounds promising, right? And when I look at the average AES signal compared to the no average AES signal, clearly I can see some valuable information here. And again, the raw signal shows a pattern, not obvious, right? And this pattern, if you look at this, is never obvious. Okay, so it's very easy to miss the point. Okay, good. So when you have that, you can choose your sweetest spot. Okay, when you have your sweetest spot, but you have to look at the trace, right? So actually, one of the key criteria here I will show you with this widget is to show five. Here I show 5 traces on that case. Up, and you can see that actually there is nothing obvious. You have some variations, but the clock cycles, everything looks very synchronous, and the clock cycle is there and it's relatively quick. Okay, so we can see that everything is the speed is quite. The clock goes quickly. What is important is to have a proper trigger signal. Okay, so you may need to go into the firmware to choose a good trigger, because otherwise you will need to align the traces together, because the analysis requires to have the traces aligned together. If not, you will need to spend time to manually or find a dedicated algorithm to align them together. It can take time actually, and sometimes a lot of times it may be difficult. Or you can use some techniques in order to overcome this. If you cannot manage your alignments, you have several techniques like working in the frequency domain. It's never great between you and I. You can use deep learning technique like using convolutional network. It may be complicated as well. Or you can use a technique that we found. The name is scatter, but it requires some expertise as well to successfully implement it. So the quality of your trigger is very important. Okay, good. Up. So why I say that quality of the trigger? How quick is an AES? Here I show an example. We made successive AES, and you can see that each pattern. I zoomed in one pattern, and one pattern can be shown here. Here we can see that we have actually 4 AES execution. Here's how this integrated processor worked. Each AES, the duration is 11 cycles or 55 nanoseconds. So you can see that it's very quick to have a misalignment. So the quality of your trigger will make the quality of your attack later on, or the time you will spend to perform the attack. To have a good trigger on an SoC device is never easy. Why? Because you launch the AES and you want to launch something on the GPIO, but they are not very synchronous. You know, the scheduler is doing stuff, or everything is not super synchronous. So it may be difficult to find a proper way to trigger your system. Okay, and you will need the expertise embedded in the firmware in order to find your way. And there is a bit of a trial and error approach as well. And so you will find the proper way by doing some experimentation. So it takes time, but it's worthwhile to take this time. Goodie. Challenge number 3. This one is just to open your mind on something that will look obvious. And an SoC device is doing a lot of things. It's not only doing the crypto. So when you launch a crypto, the rest of the SoC device is not sleeping, right? The SoC device is doing a lot of other things. What I wanted to show here is to highlight some phenomena that we faced and are, I would say, insightful. So here the first thing is when you want to analyze software, some software execution, you have to bear in mind that if you're on a Linux-based system, you have a governor. And the governor can be set. And you should set it in a proper way. So you need to have the privilege for that. But here I show 2 pictures, the very same code with 2 different settings on the governor side. On the left, it was set with an on-demand. Feature. And on the right, the very same code, but the governor was set on performance. So performance is I will use all energy necessary to execute the software. And we can see that actually we have a nice, it's a regular set of executions. The patterns are regular, so they are exploitable from a sidechannel perspective. If you're on demand, here the energy will be managed. So at the beginning you have quite a lot of energy provided, but after that the governor will give less and less energy, and you will face an heterogeneous execution, which is not optimal at all from a sidechannel perspective. Actually, it's very harmful for the analysis. Okay, so we have to think about this kind of thing. A second example, this one I like it because on SoC device you have many cores, okay? And when your software is being executed on one of the core, you may believe, okay, so number one, I need to make sure to send to the same core my execution, because when I will do my multiple execution for each of my measurement, right? This means that I need to have the control of this, because you imagine that if you put your probe on the core 0 and actually the execution is done on the core 1, core 2, 3, 4, and so on, it's problematic, right? So you need to have the control where you send, on which core you send your execution. Number one. Number two, actually, you may have the choice. Are all cores equivalent? Here I have an example. It was an SoC with 8 cores, and we made some specific analysis here. So on the top, you have, let's say, the cartography of the ES running on each core. And at the bottom is more a differential analysis. Okay, so we are going to stick only on the one at the bottom because I think it's more valuable and it's easier for the eyes. So here we send out the AES execution on each core. So on core 0, core 1, until the core 7. Each time we made the corresponding analysis. And we looked at the sweet spots. If you look at this, you can see that actually on the picture, it's quite easy to see that depending on the core, I don't have the same strength. I won't have the same quality of signal. So if I look at the core 0, I have a clear sweet spot. This is the brightest actually. But when you look at the core 1, it doesn't look great, right? It looks actually faded, okay, and spread. Same thing for core 2 or core 3. Core 6 gives a better outcome. This means that if I want to maximize my chances of doing a successful attack, I should definitely choose the core 0 in that case. Okay? And I need to, as a side note, you can see also that when you send everything to the core 0, look at the core here. There is on another core, which is the core 1, there is still some activity. So it's not because you send on the core 0 that you have no information on the core 1. Okay, it's much faded. Yeah? It's much limited in terms of information, but it's there. It's quite interesting to see that. So you have some kind of interleaved relationship inside the design, which is not surprising. It's all about electronic and physics, right? Good. So something to think about. I could talk during hours about this, but I don't have a house with you today. But some other thing to think about. So each time you make an analysis, before doing the analysis, you have to think what will be my best condition to do my analysis. How I can remove as much as possible the noise or the adjacent activity. One activity that is very overwhelming is a DRAM access. So typically try to avoid the DRAM access. Okay. A second thing, if you have this opportunity and you want to do a proper analysis, try to be on a bare metal configuration. Bare metal means no operating system. You go straight on the chip, calling the specific registers. It's not all the time possible, but if you can do that, you will have the maximum of privilege. You will be able to disable or to set proper configuration, like the clocks, like the cache mechanism, and you will be able to play with these to be in the best condition. It can make a tremendous difference. And remember, when you find the recipe in identification, after that, you can make it more complex in exploitation. Okay? Because you know what to attack, where to attack, and how to attack. Finding the where, the how, and so on, you may choose to be in better condition. Good. So that's great. So let's say I have traces, but now I need to find a way to attack it. So here I show an example. It was taken on one device, and if I want to attack, here is up, I will launch the attack. You may be disappointed, even so, you think this should not be protected. Here I show that on this example, without explaining you all the detail of this graph, but I would say you don't see any outstanding value over the 256 key guesses I made. Okay, on this graph, I'm supposed to have one outstanding, which is, yes, I'm sure this is the value. If there is none, actually, we are unable to retrieve the secret. And you can do that. It's a straightforward attack, because you may need to go to have a bit of experience, but to understand the algorithm and make some guesses how it is implemented and what will be the leakage model of this specific SoC. So here, what I want to show is it's maybe valuable to try some other things, and here we try a naming distance between the outcome of the last round and the anti-penultimate round. And if we did that, up, is what I did. Okay, oopsie. Okay, here, because I needed more information about the device, I have to do a specific attack, which is what we name a monobit attack. So what instead of estimating 1 byte, I am estimating 1 bit of the key. Okay, and because each one is 8 bits, I can make 8 attacks in parallel. It's exactly what I'm doing. So it takes a bit of time, but it's still reasonable here. And we'll see with the results that up in a few seconds the result will appear. Check. Okay, here we go. Good. Here I have my 16 words, and I guess I don't need to show you that one value for each of them is outstanding, right? So on the left you have the final outcome, and on the right you have how is my criteria when I am adding more and more traces here, or more and more messages here, because we are averaging a lot of traces for each message, but here I have a total of 5,000 messages. When I reach this 5,000, we can see clearly for all the different keys that there is no doubt of what is the key value. And I can retrieve the 16 pieces of the secret key, and as a result, I have the full value of the secret. Okay, and this in a relatively easy manner when, again, I know how to attack. Good. Let's go back. So that's it for the side channel. And what I would like to talk to you now about is about the laser. So a fault injection using a laser. Wow. Okay, laser attack on SoC. Okay, you may think that I am passionate, but this is clearly excessive. Who can do a laser attack on a SoC in a car, right? It looks like why considering a laser attack on a payment card in the supermarket? Nonsense, right? You're right. But remember, I'm not talking to hackers. I'm talking to people taking care of security. And for people taking care of security, you may consider all the different ways to create a logical fault using a physical disruption. So the first one, the cheapest one, is a power glitch. This one may be used by hackers actually because it's quite cheap. I would say I put a budget of less than 5 kilo euros. You can even find for less than 1 kilo euro if you want. But I would say a lot of people will be able to buy this kind of equipment in their garage. Okay, setup is relatively easy, but the efficiency will be weak. It doesn't mean that you cannot find something. What I said, the efficiency is weak for one reason. If you do that, you have no control of what you are doing. Remember, the SoC device is doing a lot of things. And if you induce a power glitch on one of the pin of the device, you have no control of what you disturb, right? So you have the control of the time, which is quite important. You have the control of the time, but you don't have the control of which parts of the device you are going to disturb, right? So it may work, it may be efficient, and some hackers were able to actually to find some valuable results on some devices like PlayStation or Cisco phones in the past. Another technique, more recent, consists of injecting electromagnetic pulses. Okay, so a local electromagnetic disruption near field again. That one, from a hacker perspective, is still affordable. We are talking about less than 10 kilo euros. Here, compared to the power glitch, with the EM injection, you can have a more local disruption. So that can be interesting. And you can expect to go through the packaging as well. Okay. If you want to create the expertise in-house, my piece of advice would be to avoid the garage setup. Okay. Usually, you will need a budget between 50 to 100 kilo euro in order to have a proper setup in-house. Why? Because you want to have a strong opinion. So the guy in the garage has time. He can make mistake, but statistically, all the guy in their garage, one will find something. Okay, but you are not all of them. When you are in-house and you need to create your expertise, you want to go straight to the result. Okay, so don't spare money here. Make sure that you have a proper setup. Number 3 is the laser. Laser, you need to have a direct access to the silicon. This means that you need to depackage your device, and it will leverage the ability, because silicon is susceptible to light per the physics. So a laser pulse may disturb locally and very efficiently your device. So in terms of control, a laser is fantastic, right? In terms of location, the size of the pulse, the control on the pulse, the coherency of the pulse, and the timing. I think this is very much what you can do the best. So in terms of efficiency, obviously you reach the excellence here. The setup is, I would say, relatively complex. Actually, that's not that complex. Well, you may say that I have been doing that for the last 20 years, but that's still okay. But this is clearly a lab equipment. I would say in terms of price or budget, I would consider more a budget of 100 kilo euro, and you can go above if you want to do more sophisticated attacks. Okay, with 2 laser pulses, with some other equipment. Okay, but the ballpark figure is around 100 of kilo euros. Okay, so let's be clear. You're absolutely right. A laser attack on the field is nonsense. I agree with you. So number 1, some attacks don't need all the time to be done on the field. What I mean is, I can be in the lab, and maybe there is a secret, like a key that will be the same for a lot of different devices. So I can spend a lot of energy, time, and money in order to retrieve this golden key, if you're on master key. But I would say a step ahead. If your question is, you want to make sure that your code or your device withstands faults, and you want to have a tool to stress your device and the ability of the device to have the proper behavior when it's being faulted, to make sure that, to characterize the strength of your software or your hardware protections, there is it's a no-brain discussion here. Go for the laser straight away. Because if you calibrate or if you characterize your hardware or your software with a technique like the power glitch or the EM fault injection, you won't have the confidence that you will be exhaustive. However, if you take the laser, and yes, indeed, your device seems to be protected against the laser, you have a good confidence that it will withstand attack using power glitch or EM injection. Thinking like this, in my opinion, is obvious that you should go to a laser. Something important to bear in mind, in my opinion. So, if we compare to the side channel, here, no, the risk is not in minutes. I would say a few hours may be necessary for a non-protected device to, I would say, exploit a fault. Okay. On the other hand, we can say that the attack surface is much larger than a side channel also, because it concerns any sensitive code, like a sensitive comparison. Do I have the right to do this operation or not? You know, all these critical if-else. Or you can think about a boot code and so on. So it concerns all authentication, verification, or security activation. So the attack surface is, again, much larger. Good. Practically, what is a typical laser bench? So we are working together, Ishan is working together with Alfanov, a best-in-class in laser and optics. And yes, the laser and optic is of tremendous importance. Why? Because SoC device is big, but the gates are small. So you need to have a very good quality of pulse, of laser pulse, and a very good level of control. You go for the best tool to challenge your device, but the best tool will require to have a good optic and laser system. So it will be typically with infrared light and camera, because again, everything is done in backside, and you may not know, but silicon is transparent for infrared. So this means that you can have a very good level of observation via the backside, and your laser will be able to have no obstacle in order to challenge the active area and create the photoelectrical phenomenon on the gate at the gate level. Second, you will need XYZ stage, because you will need to position your spot in a proper way to do the scan. PDM is the laser source. Typically, people are using 900 nanometer kind of laser wavelengths, okay? But and some are using the 1064, which are typical values for doing successful attack in backside. Don't go too high for laser fault injection, because after that the photoelectric phenomenon is decreasing a lot. The OptiSpot is the ability to focus defocus the laser spot, to have the control of the spot, is super important. Why? Because when it's manufactured, a SoC device is quite big, and actually at the in the micro world, the quality of the surface is never absolutely flat. So if you have a lack of flatness, your laser will be defocused when you will move your stage. So with the OptiSpot, you can control that, and have the control of a consistent spot on the die surface. You will need a scope, because you will need to monitor and use a sidechannel technique to understand, to monitor the internal execution and choose precisely when you want to sense your pulse. So the timing will require to do some sidechannel analysis. Okay, and DUT is your device under test. Good, and obviously you need a software in order to make sure that you can control the equipment, make sure that you have a good way to do the multi-parameters research and find the proper set of parameters able to disturb the chip. So, okay, from the picture to the real life. So this is how a laser bench looks like. So that's not massive, as you can see. It's still a reasonable bench. And obviously you need an enclave, because the laser can be harmful for your eyes. Good. So when I am able to create to be in condition of disturbing my chip with the laser, I need to make sure that I will be able to create a logical fault. And you have so many parameters. So it's a bit like looking for a needle in a haystack. So when I was working on this presentation, I found that this Italian artist actually did look for a needle in a haystack as a art performance. I don't know how many days he spent, so it's one picture of the guy doing this. So in our world of fault injection, you will need automation in order to cope with the multi parameters to scan. So multi parameters: the location x, y, the time, the when, all the laser pulse characteristic, the power, the duration of the laser, the wavelength, the focus, and so on. So it's a lot of things to explore. So you will need a lot of automation. Remember to manage the flatness of the SoC. I talked about that just earlier. And keep in mind that the spot side must fit with the fine technologies of SoC. So the micrometer is expected, right? So forget about multi-mode laser diode or DPSS. No, that's not good because it will be far too big compared to the number of gates you want to stress. So the finer the spot, the better your attack or your analysis. And today we are near the micrometer. And remember, 1 micrometer is more or less, remember my resolution, what I said about resolution of the probe. Micrometer is quite good because you will need to do fine faults. So it's super important. Again, the execution timing must be finely controlled. Similarly, as for the side channel, you will need to go to the firmware and you will need to have a very good control to trigger your laser pulse. And you have to acknowledge that looking for all these kind of things will take time and expertise. A typical time, recently we made an attack in our lab. It took us 8 weeks to find the point. 8 weeks. So that's quite a lot because you are trying a lot. It doesn't work because you are not looking at the right place and the parameters. It takes time. It takes time. So you have to assume that because it's a big research. However, when you have found the point and the corresponding parameters, you can go quite quickly to the exploitation. So don't think about the time for identification to consider your risk. Think time also for the exploitation. It's super important. Good. So I will show how we can get faulty ciphertext. Okay. So imagine that by 8 weeks, so let's say after 1 week of scan, you have a lot of data to process. And to avoid to be overwhelmed, actually we developed this kind of heat map with cartography, where so here it was a unsecure AES execution on one of the core, and here we did a scan relatively local, and you have and you can see each time here on the right how many faulties. So here I have no faulties, so here there is none. Okay, you can see the none because everything is as expected. Okay, and we can oops, zoom here. Okay, and you can move to the point to the other, and actually, well, there are here for instance, I have a point. There was a sweet spot from a laser fault injection perspective, so it's very accurate. As you can see, it's quite small, where I found a lot of different faulties. But the different locations where we were able to do faulties are not that many. You can see that here I have some, but if I am on the left, here I have none. So it's quite difficult to find, and there are only a few spots where you can indeed find some faulty ciphertext, because our purpose here was to fault the ES execution and collect faulties. When you have some here, like here, you can go to the next level. Here, Here we go. Here is an example. It was taken from one of the points that you could see just beforehand. And here we show for those who are familiar with AES, actually you want to induce a fault at a specific time of the AES execution. If you do that, you can exploit the faulty ciphertext and you can apply what we name a differential fault attack, or DFA. Okay, so what you can see on this illustration is that, because here we know the key for the purpose of the analysis, so we can make the difference between the expected values and the values we got. So you start by the end, you have a faulty ciphertext, you make the difference. Each time you have a difference, it's a red, okay? And you have all the time 16 bytes. So this is why you have 16 bytes here. After that, we can see how this, where does do these 16 bytes come from, and up we can go back in the round, and we can see that here, typically for this faulty number 4, there was a logical fault induced at the round 8. Okay, one single byte. Okay, and we can explore. Here we have many. Here it was this specific byte. Okay, and another one if you want. Up. Here it was this one. When you are able to do that, you can. There are valuable faulty, and only 4 faulty ciphertexts will lead to the secret key. So when you know, remember here, I had a lot of different faulties. So this means that if they have the right properties, you can, once you know where to attack, it can go very quickly to find the secret. You don't need a lot of them. Okay. So I go to the conclusion of my presentation for today. So I think it's very important to understand that attacking or finding the recipe on SoC, so doing the identification, is seldomly quick and easy. I talked to you, it took us 8 weeks for this laser, but when it goes to a sidechannel, you don't know anything about the SoC, classically you will spend 4 or 5 weeks of effort in order to find your way. So it takes time. And it requires multiple expertise. Someone specialist in the firmware, someone specialist in the sidechannel, someone specialist in whatever, but you will need the multiple expertise. And different techniques may need to be developed in order to find your way. So it looks like complexity, right? But you have to understand that this complexity is to face the fact that it's big. Actually, it's big, but once you know where to put your fingers, so once the recipe is found, exploiting may not necessarily be a big deal, depending on the level of protection, obviously. And this is what you have to keep in mind for your risk analysis. So we could see that excluding the sample prep, if you want, it can take a few minutes to a few hours in order to find the secret. And the equipment remains relatively simple for sidechannel, a few kilo euros in exploitation for the hacker side, and relatively affordable for fault injection. But at the end, when you look at, when you think about the business related to one chip, imagine you have a specific device, and when you see the amount of money that one device generates over the world, the price to challenge the security is super small today compared to the price that this device generates over the world. So in my opinion, it's worthwhile to spend this money today, because what is at stake is far too big. If your device is weak from a security perspective, you will need to cope again and again to justify why it was not that resistant. So in my opinion, it's worthwhile the investment, both to build your expertise in-house and to consider the proper protections. In terms of protections, I would say I use the word intentionally of mitigation at the hardware level. So you can mitigate the risk at the hardware level. Typically, you won't put a laser sensor or light sensor all over the chip surface, or you won't put crazy things all over the surface. It's unaffordable, right? But I think there are mitigations that can be done. Sometimes locally, you can put some redundancy, hardware redundancy, in order to make sure that you can detect the fault. You can put some algorithm protection, logical protection when you have protected, when you want to protect a cryptographic functions or a cryptographic accelerator. So the techniques are well known. You just have to apply them. Typically, you have to mitigate as well by putting a minimum will be to protect against the power glitch. It's very local. So you can filter or you can detect if a glitch was sent to one of the inputs of the device. At the software level, for me, it's a very must. Because you know that you have, when you know that you have a sensitive asset, you have to put protections. Even so, the SoC manufacturer claims some security, put additional security on top of it. It's a good practice from a security point of view to have a different layer of security. So the embedded software should take this into consideration, and the software knows what is sensitive or what is not. All in all, my personal opinion is that security protection are not an option. Because otherwise, someone will try to find the Graal. And you will always find someone to make the quest. I really thank you for your attention. And I'm open to any question you may have.
So, first of all, thanks to take us to the journey in the interesting world of silicon attacks. I think it was a great presentation, and you present a lot of experience and insights, which makes really value in our community as well. So we received also some questions. Let's start with some technical questions. Could you try to explain what exactly happens in the silicon in case of a laser pulse would be shot on it? Is it like adding electrons, or maybe you can try to explain it a little bit?
Say it again. Sorry, the question, Sven. Can you say it again so I get the point?
The question was, can you try to explain a little bit more detailed what happens if a laser pulse is shot to the silicon?
Okay, sorry. So first, you have to imagine in the micro world that the pulse, it's an infrared, so it will go through the substrate, right? And it's quite transparent. At some point, the pulse will touch the active area where you have the N and P gates. And here, at this level, it will create some photoelectronic phenomenon. This means that you will have a local current created because the laser brings energy, and the energy will be captured by the electron. And because it's a semiconductor, the electron at the I don't know the word, but the electron will jump to the conducting area and create this current, the local current. And the local current at the gate level may create a disruption. I hope I answer this in a proper way.
Yeah, maybe it is also going in some physical deep.
It's physical. It's a physical phenomenon, but it's not a super difficult phenomenon. Yeah.
Yeah, but thanks for explaining or trying to explain. Then the next question: do you have experience if it makes a difference if the chip has an hardware trust anchor in place, like an HSM or an TPM?
It all depends on how the TPM typically was protected. I would say, and you have to look at what were the claim of the manufacturer with regard to this specific attack. So it's not because it's a TPM, trusted platform, that it's secured against these attacks. You have to look for the claim, and sometimes some made the effort to go to a certification like a common criteria, and here you can increase your level of confidence. But I will give an example, something maybe more dedicated to the SoC world. If you have a trust zone doesn't mean that it's resistant against fault injection or sidechannel. Not at all. Trust zone is just a technology where you have a segregation, logical segregation between an operating system, a rich operating system, and a secure operating system. You can manage that, but that doesn't mean that you are resistant against this kind of attack. So each time it goes to security, it's good to go down to the details of what is claimed in order to make your own opinion of where you can be confident or not.
Okay, thanks. So I also think, when I understood it correctly, your attack is more on the AES engine itself. And for example, an HSM, which has inside a key storage, store the keys there. But if they want to make some cryptographic operations, then they use also the AES engine and
Yes,
have to put the key there, and then your attack works again on the AES engine itself.
yes, true.
Okay. So then there comes also a question, do you see an industry adopting evaluation standards for DBA and FI, or do you have information that maybe such kinds of verification mechanisms will be recommended for some industries?
But today, you have some industries that made the effort to put some clarity about providing some certification scheme, if you want.
Mm-hmm.
And when you go to a certification scheme, you go to a lab that will be the independent party to stress your device and say if your claim are right or not with regard to the resistance to this kind of attack. So as part of the different schemes, you can find the highest standard is related more or less with the common criteria. Even so, you have different levels, common criteria EL3, 4 plus, and so on. 1, 2, 3, 4, 5, 6, 7. The big drawback of common criteria is it takes a lot of time and is quite complex to. It's very much an effort. But this is, I would say, the best standard for this. Some other standards were created, like ARM had this initiative with PSA certified, where actually you can challenge your product. It's more for SoC device, that one. You can change the security of your product with this private scheme. So again, here you have to go down to different standards, but there is a lot of work currently, and typically in Europe, within the cyber height, the ENISA is working on making these standards more readable and extend them to more products.
Mm-hmm.
So it's work in progress.
Okay, thanks. We received also some questions regarding possible mitigations. Maybe first an idea from my mind. What do you think? I think a very good mitigation, risk mitigation to protect the devices against such kind of attacks will be if you would use device-specific keys. So because then it makes no really sense to spend the effort to take out a key, because on a similar device, for example, on a vehicle of the same brand and the same platform is not working anymore. You can nothing to do with it. Is this one of a good mitigation?
I would say this is one mitigation, definitely. So this means that doing that, having one specific key on each device, this means that the value of the key decreases quite a lot. So you have to think, what is the cost to manage this? Some manufacturers are struggling to do that, but if you can manage this, it's definitely a medication. However, I would say there is still a risk, but it's more at the reputational level. If someone can demonstrate that someone can extract the secret key using one of these attacks, you may claim that no, it's okay because it's one device per unit, but you are at the justification level, and I would say the reputation is quite damaged already. So I would say it's one mitigation, but I would personally I would not rely only on this.
Yeah, I agree. So there is another idea from the audience. The question is, will key wrapping inside the HSM maybe help against this kind of attack?
Key wrapping? What does that mean exactly, key wrapping here?
Key wrapping, I think it means that you change the key between the operations, and you use also sometimes keys which has no real effect, only by
like session key or a limited a key with limited usage. Yes, it's a mitigation that can be very powerful. It depends how many times you can use the key. So for sidechannel, definitely you will need quite a lot of execution with the same key to retrieve the secret. So that, going to that at the cryptographic protocol level, yes, you can protect yourself. For fault injection, think about that only 4 faulties can be necessary to retrieve the secret. So at the end, it's a way to mitigate the risk to have this kind of cryptographic protocol. But bear in mind that at the beginning, there is always a master key. And this master key can be changed every time. And so the attacker will go to the master key if he can. So this is how you build your system, and it's up to the people designing the system to think about this.
Yeah, you are right. Then a question where I guess you can answer very simple and quickly.
Oh yeah, the pressure now.
Which attack has more attack surface without decapping the chip? Is it fault injection or SCA?
Without decapping, you have the EM fault injection, which will have the bigger attack surface. But remember that sidechannel is focusing on cryptographic algorithms. So on something very, very valuable also. So I would say do an exclusion between either sidechannel or fault injection. So again, I would say sidechannel can be operated without decapping because you can put your probe on top of the packaging. You have a bit less, but it's still valuable because the packaging is never very big. First, and second, when you go to fault injection, the EM fault injection theoretically can manage fault through the packaging. Practically, it requires quite some expertise, but a lot of people are working on this on this technical area today.
And then we received the question for SoC instruction skipping. Is there lasers are used, or is it mainly just power glitching?
A bit laser or power glitching used for,
For SoC instruction skipping.
Actually, both can be used. Again, it depends how powerful you want your tool to be. You can still do Berlin to Stuttgart in bicycle, but if I tell you that you have a fast train, you will check the fast train, right? Yeah. Okay, it's more expensive. Unless people can afford the fast train. But if you want to skip an instruction, either can be used. It will very much depend how much you can fault the device, and for this one, you have to go to the experimentation to see it.
Okay.
But think about train is faster than bicycle.
I agree totally. From your experience or what you have just seen, what is the most seen motivation and how big is, from your experience, the motivation for an attacker to do such kind of an attack?
But there are two kinds of motivation. The one is to exhibit something and to exploit this. Okay, I think some devices have been severely harmed by for their. There was this gaming box. I think it was a PlayStation, if my memory is good. It was one of those. But I think the biggest one is, in my opinion, is a reputational damage as well, because that one is very hard to quantify. But imagine you have a chip or you have a device, and this device aims to be on the field for many years, because you cannot afford to design a new chip every 2 months, right? It's not software. When you know that there is a security flaw, a potential security flaw, that's a lot of money that you will spend, and people won't trust, may not trust your device, and here you start to struggle and to sweat. So the motivation of the hacker can also to harm the reputation.
Mm-hmm. Okay, thanks for sharing this. Then I would say, let's come to the last question for today. Do you recommend any paper or some resources regarding software firmware mitigation methods against such kind of attacks?
That's a good point. I remember I wrote an article a long time ago, but I'm not sure that it will be enough. I made a survey on fault attack, but it was very much targeting a secure controller like smart cards. I don't have any good publication in mind, to be fair, for someone who wants to know all the mitigation for this kind of device.
Mm-hmm. But
So
maybe we can also try to do this, that you think afterwards, or you
yes,
try to find something,
yes,
send it to me, and then I will
yeah,
present it to the community so that they
yes,
can find some more information on
yes,
in some resources.
yes, that will be helpful for me for tonight.
Okay. So, okay, then I would give you the stage back to make some closing words in the direction of the audience.
So here I hope that I try to convince you about. I would say yes, you should consider this kind of attack. If you need to build the expertise, or if you want to grow in this expertise, feel free to contact Ishan, because we are our activity aims at helping people, supporting people to go to the next level. So either to build your in-house expertise, or even to get some training, or or if you need to use our expertise lab, we will always be keen to bring you to the next level.
Okay, then from my side to you, Hugues, thanks again. It was a great presentation. To the audience also, thank you very much to be with us. I hope you enjoyed the presentation today. And I hope also that we see us during the next weeks again with another interesting talk. And then I would say goodbye for today. Have a nice evening. Have a nice day wherever you are in the world. And see you again.
And thank you very much to all of you. Bye bye.